Okay. Good morning. Welcome back to the natural language processing class. So for this week, let's continue to look at structured prediction. So for the previous 2 weeks, we discussed generative and discriminative models for sequence labeling. But structured problems are beyond sequence labels. So for this week and the next, we will see 2 more types of structures. And we will see how the modeling techniques can be adapted to different structures. So for today, our topic is sequence segmentation. So we will have 4 topics. The first one is how do you define a task? And what are sequence segmentation tasks? And the second topic is we can use sequence labeling methods to solve sequence segmentation. We reuse whatever we learned in the previous 2 weeks for this week. And the third topic is we move on into building log linear models for sequence segmentation itself. And finally, we will discuss large margin models like Perceptron and SVM for sequence segmentation. So first, let's review the task. The goal is that you're given a sequence, like a sentence. You want to chunk the sentence into different segments. Right? One instance is word segmentation. So for Chinese, Japanese, and Thai, right, the input is a sequence of characters. Now you want to chop them into a word sequence so that you can better understand what it says, right? So this has been relevant in the statistical era. For now, big, like large language models don't explicitly segment sentences, but it can still be relevant to various tasks nowadays. Another task is shallow parsing, syntactic chunking. So the goal is when you're given a sentence, you try to identify what are the noun phrases and verb phrases, etc. in this sequence. So basically, when you do shallow parsing, right, you chop the sequence into a sequence of segments and then assign a syntactic label to each segment, such as the noun phrase, the verb phrase, etc. Yet another task is named entity recognition, which we saw in the beginning of this semester as well. So given a sentence, right, you want to recognize what are the person names, location names, organization names, etc. From this sentence. These are spans. And besides these spans, you also have words which are not named entities. These words are just identified as single words, labeled with O. For the named entities, you chop them into chunks, right? And then you assign labels to them. The labels I just mentioned to you apply to news. But for biomedical text, you might have like chemical names, disease names, drug names, etc. Okay. So these are 3 different tasks for sequence segmentation. And you can see that they have subtle differences, right? For word segmentation, you don't have segment labels. You just need to segment the sentence. For syntactic chunking, you have labels. And for named entity recognition, you not only have labels, but you also have some non-segment words, right? You segment the sentence into some chunks, but for the other words, you just don't segment them. So you have minor differences, but the major task is to chunk, okay? And obviously, this is different from sequence labeling, because for sequence labeling, you don't group things together. You simply assign labels to each token. All right. And because of this difference, you will see later that the modeling techniques will slightly vary. So when we introduce the task, right, we have to introduce how do you evaluate the model output. So we discussed this for text classification, right, where we use accuracy for evaluation. But for sequence labeling, we have yet to discuss it. So it turns out that evaluating sequence labeling tasks is relatively easy. You have W1, W2, say until Wn as n word, and you have T1, T2 until Tn as the sequence of labels on the word, right? So, and you have a gold sequence label. So maybe T gold 1, T gold 2, until T gold n. So this is for sequence labeling. And a very simple way to evaluate things is you just need to compare like the output tag with each gold tag location after location, and you calculate the percentage of correct tags, right? Compared with these gold tags, so you can use accuracy for evaluation. But for segmentation, it's slightly different because say you have sequence of segments, okay? So this is one segment, this is one segment, this is one segment, this is one segment, etc. Okay. But for the output, you might have this is one segment, this is one segment, this is one segment. Okay. So the number of segments can be different. Okay. So this is the output, this is the goal. Okay. This is segment gold 1, segment gold 2, segment gold 3, segment gold 4. Okay. But this is S1, S2, etc. So how do we compare these, okay, when their numbers are different? Okay. Well, you could, again, identify which ones are the same, right? Between the output and the gold standard. You can identify those. But the thing is, you don't have a denominator. Because for this, you know the number of labels, right? For this, you don't know the number of segments. So what can you do? It turns out that a metric called F measure can help you here. So F measure consists of two components. One is called the precision. One is called the recall. Okay. So what does the precision mean? Okay. Precision means out of all your outputs, what are the percentage that are correct? In other words, for precision, right, you use the matching ones, okay, to divide your model output, right? So your denominator is the model output for precision, how precise your model output is. So what does recall mean? So recall means out of a lot of gold examples, right? What is the percentage that your model recovers? So this is called recall. Okay. In other words, the numerator is still the matching ones, but the denominator is the gold ones for recall. Okay. So if we call the matching ones SM match, then precision is the number of matching ones divided by the number of outputs, SM versus S. So the recall is the ratio between SM over SG, the gold ones, okay? So SM means the matching ones, okay, the number of matching ones. So once you have precision and recall, you can define F score as 2 times precision times recall divided by precision plus recall. Okay, so you can easily see that if both are 100%, then this is 1. Okay, so if both are a half, this is a half. Okay, So this is F score, but F scores can vary. So if you pay more attention to precision or recall, you can weigh precision more than recall in your F score. If you prefer recall to precision, you can weigh recall more, okay? So this balanced F score is called F1 score. So if you see in some papers, F1, subscript 1, it means that you use this equation. So I give you one example in word segmentation. So next slide shows one sentence, okay? The sentence has 9 characters, and the gold output is segmented into 7 words. Now suppose that your system output, right, confused the 4th and 5th character, because this is a word, right? But this is a word. But in this context, it should not be 1 word, but 2 words, okay? So your system output has a length of 6, okay? So you match the system output with the gold output, you found that 5 words are the same, okay? So SM will contain 5 words. And so the precision is 5 out of 6, okay, for your output. And the recall is 5 out of 7, okay, measured according to the gold output. So your F score will be calculated according to the equation. It will be something between 5 out of 6 and 5 out of 7, okay? So it's sort of a balance between precision and recall. Okay, so now we learn the task and we learn how to evaluate it. Now let's move on, okay, to how do you solve the task using sequence labeling. All right. So for sequence segmentation, basically our goal is to segment the input sequence. However, some clever researchers realize you can transfer the segmenting actions with label sequences. The basic idea, right, is to make decisions on each input token, each input word. You decide, okay, whether I should segment it from the previous word or attach it to the previous word, okay? So it's sort of a binary decision. So I give you an example where the sharp, each sharp means a token or a character. The sequence has 6 tokens or characters, right? And the first 3 makes a segment, the middle 2 makes 1, and the last token makes a segment. So if this is the case, and if we use S to denote, we separate the current token from the previous one, and A to denote that we attach the current token to the previous one, the label sequence can be SAA for the first segment, right? SA for the second segment, and S for the last segment. And therefore, we turned the segmentation problem into a sequence labeling problem. We can use sequence labelers, right? Models we learned in Chapter 7, Chapter 8 to solve the problem. Right. Let me give you another example in the next slide. Okay. So the input sentence consists of 5 characters. You could do word segmentation, or you could do like part of speech tagging. Okay, so for part of speech tagging, your input will already be segmented, okay, as shown in the first row. So all you need to do is to assign a part of speech label on each input, right, on each word. So the first word is a like pronoun, the second word is a verb, third word is like function word, the last word consisting of 2 characters is a noun. All right. But for sequence segmentation, okay, suppose that we still have 4 words, my apologies, and you need to chunk the 4 words into syntactic chunks. Now you realize that the first word, okay, meaning I, a pronoun, so forms a noun phrase, okay? And the other 3 words, okay, means have eaten an apple, right? Forms a verb phrase. It's 1 chunk. So how do we solve the problem? We can still apply the segment and attach labels for this one. But this time, okay, let us make the labels more refined. Rather than using 2 labels, segment and attach, to differentiate each input word, right? We differentiate single character words, single word chunks as S, the beginning of a multi-word chunk as B, okay? The middle word in a multi-word chunk as I, and the last word in a multi-word chunk also as I. So because of this, okay, you can find that in the last row, the labels, the first word is an S because it's a single word chunk. The second until the 4th words, right, they are B, I. Why? Because they're beginning and not the beginning of a multi-word chunk, okay? So we use the 3 different labels to denote a single word chunk and the beginning or non-beginning of a multi-word chunk respectively. So we extended S and A into S, B, and I, okay? So why do we do this? This can make, right, our sequence labels more expressive, right? When you see a B, you never know whether this B is also the end of a chunk or not. Okay, you have to look at the next tag to know. But if we differentiate B into B and S, you know whether there's a single word chunk or multi-word chunk beginning. Okay. And if you take a closer look at the BII, okay, labels, they're attached with another label, which you know are syntactic categories, where VP means verb phrase, okay? So this is unique to the syntactic chunking task, okay? You attach the segmentation label with the syntactic category label to both denote, okay, which chunk it belongs to and what's the category of the chunk, okay? By having these 2 sorts of labels, you're doing chunking and chunk labeling simultaneously. All right. So this is a second example, a more complex example. All right. So next slide shows typical labels that we use, okay, for solving sequence segmentation tasks. You can see that for word segmentation, for syntactic chunking, and for name entity recognition, the label sets are different. Why? These are empirical. Now, people have shown that if you use these label sets, you will get better results. Okay. If you change the different label sets, maybe your results are slightly worse. So these are what are summarized as useful labels from academic research, from the literature. So let's first look at word segmentation. What labels do we use? We use a set of BIES, 4 tags, okay? Where B means the beginning of a multi-character word. I means the internal character of a multi-character word. Not the beginning, not the end. E means the end of a multi-character word, okay? And S means a single character word, okay? So, if you still have something like this, if you still have something like one character, one character, one character, one character, one character, and one character as a sentence, so this will be B, this will be I, this will be E, this will be B, this will be E, this will be S. So you use this label sequence to denote the segmentation pattern of this sentence. Okay, this is more expressive but compared with S and A, okay, because you know the word patterns now, just by looking at the labels, right? These will determine the features, the expressiveness of features, which we will look at later. After you look at the features, you might get a better sense of why labels matter, okay? For syntactic chunking, it turns out that two labels works. You just need B and I, okay, which are analogous to S and A, right? So B means the beginning, I means not the beginning, or B means separate, I means attach, okay? But for syntactic chunking, you need syntactic categories in addition to the segmentation labels. So at the end of B or I, you also want to attach whether this is noun phrase or verb phrase, etc. Okay. In the end, your label is a composite, such as B, MP, etc. For named entity recognition, it turns out that you can have the BIES tag set, so which is similar to the word segmentation tag set. But you also have an O tag. What is the O tag? O means that the current word is not a named entity. Okay. So when the chunk is not a named entity, it's irrelevant. So you use O to tag this word. So similar to chunking, right? So these segmentation labels must be attached with the named entity categories. So rather than having BIE, you say B-X, where X, it could be a person, could be an organization. All right? So this is the label sets. Okay, you have a taste of what people do. And it turns out that if you transfer a sequence segmentation to sequence labeling, you could already get quite nice results. Okay, so this is not a purely theoretical problem setting. This is a practical setting. Okay. Now let's build models. It turns out that generative models, they don't work quite effectively for sequence segmentation problems that we just mentioned as discriminative models. So for this class, I will only introduce discriminative models, okay, because they have rich features. So let's recall discriminative models. We learned them last week, right? So their parameterization is completely based on feature vectors. So you define a set of features to represent the input-output pair, okay, global feature vector. For the input and output label sequence, you define that as phi, okay? I use X to denote the input sequence and T to denote the output text. So phi xt will be the feature sets we extract. Okay, it's a long sparse vector. And the parameterization is to attach a theta, define a theta, to score each element in phi. Okay, and your score is theta dot phi. So we learned it last week. And of course, you can decompose phi. So by assuming Markov assumptions, right? So each label is dependent on only k labels before it. So if k is 1, this is first order Markov assumption. Okay, k is 2, second order, etc. So after you have these feature independence, you can define feature templates now. Okay. I give you one example. So when you have a named entity recognition task, right? The input is he visited New Zealand. So he and visited are both O's. They're not named entities. But New Zealand is one single named entity. So this new is the beginning of a location, right? Zealand is the end of a location. So you use these two labels. And when you extract features, right? If the feature template is WI and TI, the current word and current tag, you can get this large sparse vector, right? Where new being tagged as the beginning of a location has a relevant element as 1. But new having the end of a location, or new or old, right, having the beginning of a person, they are both zeros because they don't fire, okay? Their feature vector contains all word tag compositions, right, because they are feature instances, possible feature instances. But for this input and output pair, only those that exist in the input-output pair are 1s. Others are zeros, right? So we discussed features in chapters 3, 4, and 8. So here I show you the sparse feature vector again. Now with this understanding, maybe we can take a brief look at what kind of feature templates we can define, right, for the 3 tasks, the 3 sequence segmentation tasks. Let's first look at word segmentation. Okay. For word segmentation, what do? You have a lot of input patterns, which are combined with the output label. Okay. What are they? Maybe you have character unigrams, character unigram. Like, what if the current character is this? Okay. And you tag the character as S. Okay. So what about you have this character being a single character word? What if the previous character is that, and your current character is tagged as a single character word, right? So C minus 1 and TI. CI minus 1 TI. So what about the next character is this character, and your current character is segmented or tagged? Okay. And you can also have character bigram features. What about the previous character is these, and the current character is these? What about these characters are put together, okay, in the input sentence? And you want to segment the current character, or you want to label the current character as being part of a word, okay? Character bigrams, and also character trigrams. You know some particular trigram patterns, they only exist in idioms, right? Forward idioms. So whenever you see these 3 characters, you know that they must be together. So you know how to segment the current character. And on top of that, you could also have overlapping features. For example, you know the current character is this, and you have a type feature, whether the current character is a punctuation or not, right? And whether the current character is a number or a date denoter or time denoter or English letter or whatsoever, right? You have these category labels which help you better capture the patterns. And when you define this, this is called feature engineering. This is what students did before the 2010s. Okay. Nowadays, you no longer do feature engineering. You do hyperparameter engineering, which is more boring to me. But we will talk about them, right, from chapter 13. I'll talk about what are hyperparameter tuning, okay, hyperparameter search. Next slide shows you an example. There are 6 characters. This means among which foreign institutes are 6, okay, among which there are 6 foreign institutes. So, and we are trying to tag the 4th character, okay, we're trying to tag C4, okay, and the output has C4 as B, the beginning of a new word, okay. So given this input-output pair, and according to the feature templates, we have instantiations. For example, the first feature template, character unigrams, right? So the previous character is third character, current character is fourth character, next character is fifth character, and each of these are instantiated, right? And each of these are combined with the output label B, okay, to form a feature instance. Like 6. Okay, what if the next character is 6 and the current label is B? So C I plus 1 equals 6 and TI equal B, they're composed together to form a feature instance, right? And you can look at other feature instances, they are similar, okay? So according to the feature template from the last slide, and according to this input-output pair, we know the non-zero values in the long vector, right? Right. Similarly, you can imagine other instances. Now let's look at chunking features. For chunking, it turns out that the parts of speech are useful. So we could define the following feature templates. The first category, right, are the 5-word window, word unigrams in the 5-word window. What if the previous word is these, and the current word is tagged as this, the beginning of a noun phrase? The second categories are part of speech unigrams, right? What if the previous word, what if the next word is a noun, and the current word is tagged as this category, this syntactic chunk? Third category are like word bigrams, needless to say. Fourth category are part of speech bigrams. The fifth categories are word part of speech compositions. So what if the previous word is this word? All right. What if the previous word is can, and the previous part of speech is a noun? Okay. And the current tag is the beginning of a verb phrase, okay? The sixth category is, the sixth categories are chunk label bigrams, okay? Chunk label bigrams. So all these feature templates, the feature templates 1 to 5, okay, are all combined with the current output label. Because if you don't combine these input feature patterns to the output label pattern, you cannot differentiate different outputs, right? So the feature templates are meaningless. So you have to compose. All your feature instances must consist of the output label. This is a must, okay? All right, the next slide shows you some feature templates, feature instances. So given the sentence, Mary went to Chicago to meet her boyfriend, John Smith. So if we're trying to label meet as the beginning of a verb phrase, according to the feature templates in the last slide, we have the feature instances on the right, okay? I leave this for you to read, okay? So next, I show you some feature templates for named entity recognition. And they consist of words and part of speech patterns, of course. And they also have some like categorical patterns, such as whether the current word is from a named entity lexicon, okay? And also they have the word spelling patterns. For example, you can generalize every word into like capital letter, lower letter compositions. How do you generalize them? So you generalize every capital letter into capital X. You generate any lower letter as lower X, okay? So when you generalize, when you turn every letter into a normalized letter X, you abstract away the word spelling, but you only have the uppercase, lowercase pattern, like capital X, lower XXX, or capital X, lower X. So these are very useful indicators for entities, okay? For example, there was one language model called Elmo, right? Elmo. where the ELMs are all capital letters and O are lower letters. So you flip Elmo into XXXX, right? And you immediately guess this is likely a named entity. There can be a simplified version of this letter shape, which is you combine consecutive capital X into one capital X and combine consecutive lowercase ones into low x. So I leave it to you, all right, to review this feature template, to think about why they can help, right, in better segmenting a sentence. So next slide shows you some feature instances with these templates. You have to note that all feature instances are combined with the output label because they need to differentiate different outputs, right? If you just extract features from the input, they're useless because in the end, you want to select the high scored output. Your features must represent outputs. That's why your label set matters, right? So if you define your output label as B or I, if you define your output label as BIES, you know your features will differ. When your features differ, your high dimensional space will differ. And your model, like fitting and generalization, will change. So that's why it's you need to carefully define the features. All right. Now we have seen how you use sequence labeling models, okay, for solving sequence segmentation. As soon as you define the segmentation labels and you define the feature templates, you can throw your problem into the sequence labeler we discussed last week, okay? All right, so this turns out to be an effective method. But now, from now on, we need to look at some models that are specific to sequence segmentation. They are no longer sequence labelers. Why do we need like sequence segmentation models? It's because for sequence labeling, our features must conform to Markov characteristics. In other words, if we assume that the sequence labels conform to first order Markov properties, right? So each label will depend only on the previous label. What could be the complication? Well, your segments are not constrained to one label, right? So think about Chinese word segmentation. You have a lot of idioms, which are 4-character words, right? 汗牛充栋, right? 萧规曹随, just to name a few. They are 4-character words. So if you have a first order Markov assumption, then you can only look at patterns in 2 characters, nothing beyond 2 characters. So if you handle 4-character words, you can only guess. You can only guess. And sometimes it's very effective to guess. It turns out that if you use like CRFs, right, to label Chinese character sequences, you can get pretty good Chinese segmenters. But we want to go to the extreme. We want to make the models more accurate. So what do we do? So we want to define, right, next slide, segment level features, right? We want a feature to represent the whole word rather than just each character individually. When you do that, the character level features no longer work. We need to define word level features. All right. And it turns out that when doing so, your models will have to change a little bit, okay? In both the training algorithm and the decoding algorithm. Okay, you already know what is decoding, right? So let's look at the problem one by one. So first of all, let's redefine the features, okay? We saw the features for sequence labeling. Now let's redefine the features and then we redefine the models. Because our models are all parameterized by the vector space, right? So we need to define a vector space. So let's take Chinese word segmentation as the task and look at how to define the features. Let's denote the input character sequence as C1 until N, okay? And the output word sequence as W1 until W, okay? We don't know how many words are there, because if you segment the sentence differently, the output can be different numbers of words. So further, let's denote WJ, the jth output word, as C beginning of J, BJ, C beginning of J plus 1 until C ending of J, EJ. Okay. So where BJ and EJ, they denote the character indexes, okay, for the jth word. Okay, they're functions, right? B means beginning, E means end, J is a parameter, the return value is the character index. Okay, let me give an example. If the input character sequence is these, okay, and the first character is a word, the second and third character are a word, all right. So W2, when J is equal to 2, W2 will be 昨天, yesterday, okay? So B2 is 2, why? Because the beginning of the second word is the second character. And E2 is 3, because the end of the second word is the third character. Okay? Now you get an idea. What does this function do, right? Now we can define a global feature vector phi over W. Okay? Now let's assume a first order Markov assumption on the global feature vector. So it can be the sum of local vectors. Let's take the first order Markov assumption, okay? We assume that each feature only covers the range of 2 consecutive words. That's easy, right? So each feature only covers this range or this range, okay? We don't go over word bigrams. So when we do that, we can denote local features as phi, wj minus 1, and wj, okay? And the global feature vector will be the accumulation of local feature vectors as shown in the last equation, second last equation. And further, for the convenience of notation, okay, let us also swap between 2 equivalent representations. One is phi w word bigram. One is phi character denotions. So this phi c uses character notations to denote the same feature, okay? What are they? First of all, the character sequence, C1 until N. And then Bj minus 1, Ej minus 1, Ej. What is that? This is Wj minus 1. This is Wj, okay? So you could use phi word bigram to represent features here. But you could also use phi, the character sequence. This is B, okay? J minus 1. This is E, J minus 1, right? This is EJ. Why not BJ? Because BJ is equal to EJ minus 1 plus 1. So when you know this character, you don't need to know the index of this character, right? So 3 character indexes are enough to represent the 2 words. The same. Why do I use character indexes? Because later I will derive equations, right? So let's look at one example. So given these, what are the feature templates you can extract? Well, you can extract a word and character and length, whatsoever features from word bigrams. This is very expressive. For example, I can extract the current word. Well, even if the word is as long as 10 different characters, right? I can still represent it, a 10-character word. And I can represent the word bigram Okay, 2 single-character words or 2 4-character words, fine. And because word diagrams are sparse, okay, we can define backoff features, like the beginning characters of 2 consecutive words, the ending characters of 2 consecutive words, the beginning character of the previous word and the current word, okay, or even the length of the previous word and the current word. These are all patterns in Chinese sentences. This could all be useful for us to segment a sentence. I don't have time to elaborate, but the next slide shows you one example. So this example is the same as the part-of-speech tagging and chunking one, right? I have eaten an apple. When the output is I have eaten an apple, right? I can extract the input-output pair. Why is the input and output the same? Not the same. The input is the character sequence. The output is the word sequence. Why are they the same? Because the output is just a segmented chunk, right? The output contains the input characters. According to the previous feature templates, we can extract feature instances over all the word diagrams, sliding from left to right, okay? And you also attach the beginning of sentence and end of a sentence tokens. So we extracted local features from word diagrams, okay? Every word diagram, and in the end, I accumulate all the local features together to be the global feature. The global vector is as long as the local feature vectors. They're the same length because they use the same feature instances. But the global one has more non-zero values compared with the local ones, since it is the sum of all the local feature vectors, right? So this is the same as sequence labeling, as you can compare with the last week, right? Now, after defining these feature instances, let us look at 3 models, right? We have learned 3 discriminative models. One is log linear model. One is SVM. One is Perceptron, right? And we saw in week 4, right, that they are essentially the same model, single layer neural network, single layer perceptron, with different training objectives. And we adopted all 3 of them to sequence labeling last week. Now we want to adopt all 3 of them to sequence segmentation. So let's look at them one by one. First, log linear model. The sequence labeling version of our model is called CRF, Conditional Random Field, right? So the version for sequence segmentation is called Semi-Markov Conditional Random Field, or Semi-CRF, okay? How do we parameterize this model? Next slide. So our model parameterization, okay, is the same as log linear models for classification and sequence labeling. So we define the phi, and we define a model parameter theta. Theta, each element in theta scores one element in phi, okay? So that theta dot phi is your model score of the input-output pair. Now for word segmentation, I don't need to write C and W because, as I mentioned to you, W contains C, right? So this phi is phi of W. Now theta dot phi is the word sequence score. And what we want to do is we want to find a W out of all possible Ws that has the highest score for decoding. And we find that this decoding algorithm is the same for Semi-Markov CRF and also for Perceptron and SVMs, okay? So how do we solve the decoding problem? Given an input, okay, given an input sequence, let's take word segmentation for example. How many output sequences do we have? If the input length is n, the number of outputs is 2 to the power of n minus 1. Why is that so? If you think about using sequence labeling for word segmentation, right? So each character can be either segmented from the current character or appended to the previous character, right? So the first character must be segmented. So from the second character onwards, each character has 2 choices. And there are n minus 1 characters to decide, right? So in the end, there are 2 to the power of n minus 1 possible sequences. For chunking and for name entity recognition, this number can vary a little bit, okay? Something to the power of n. But the main thing is that, the important thing is that the number of outputs is exponential. So you cannot use brute force algorithms to find the most highest scored output sequence, right? Then how do we solve the problem? Oh, we had some experience last week and the week before last. Because our model can be factored, or because our features can be factored, we could think about using dynamic programs to solve the problem. So first, how do we factorize our features? Look at the last equation here, right? So theta dot phi, w, 1 to w is equal to theta dot the sum of phi, wj minus 1 wj, okay? Where does it come from? It comes from our Markov assumption, right? Okay. Now, theta dot the sum of phi equals to the sum of theta dot phi, right? So this is commutativity of addition, right? Distributivity of addition and multiplication, right? So, and also we know this phi wj minus 1 wj notation can also be denoted as phi c, c, bj minus 1, ej minus 1, and ej, right? So we have this last equation. This is the incremental calculation steps. It's very similar to sequence labeling. It forms a basis, okay, for a dynamic program. And you all know the thinking of dynamic program now after you learn the Viterbi algorithm. So I will go slightly quicker. So the main idea is, if you want to find the highest scored output segmentation sequence, right? Can it be derived from the highest scored subsequence? Okay, removing the last segment. Okay, in the word segmentation case, right? If you want to find the highest scored output word sequence, can it be calculated from the highest scored word sequence before the last word? Okay. No, someone says no, because the incremental step has 2 consecutive words, right? So when you have the highest word subsequence before the current word, you add this additional feature, okay? You don't guarantee you get the highest word sequence until this word, because you might have a suboptimal previous sequence with a different last word, okay? And that different last word, when added with the current last word, forms a word bigram. And this word bigram can give you a very high local score, incremental score, which makes your your suboptimal subsequence leading to a higher scored full sequence. Okay, how do you solve the problem? We had experience for sequence labeling, which is we don't find the optimal subproblem absolutely here. We find the optimal subproblem with a condition, right? With what condition? The condition is the last word, okay? Rather than storing the optimal subsequence ending with any character, okay? We store the optimal subsequence ending with any character and with a specific last word, okay? This is called a dynamic program signature. Slide 31. With this understanding, we can try to build a table, okay? With this optimal subsequence being denoted as W hat, okay, B, E, where B denotes the beginning of the last word, E denotes the end of the last word in the capital W sequence, okay? So if we don't store B, we only store E. It stores the highest scored subsequence until character E, right? It doesn't contain the signature, which is the last word from B to E being a word, okay? But in addition to E, if we also store B, okay, we end up with a table. This table contains a subsequence from the first character until character E, but with the last word being CB, CB plus 1 until E, okay? So we form this signature. And this picture, okay, shows you the incremental step from W hat B prime B minus 1 until W hat BE. In other words, you can prove, okay, if you know W hat B prime B minus 1 for all B hat, for all B prime, okay, you can find W hat, the optimal sequence with signature BE, okay. You only need to enumerate B prime, okay. And in each case, you go from W hat B prime B minus 1 to W hat BE by adding the incremental feature, incremental score. What is the incremental score? Next slide. The incremental score is from W hat B prime B minus 1 to W hat BE. The incremental score is exactly this B prime B minus 1E, this word diagram, feature and model parameter. You can prove it, right? You can prove it in the same way as you proved the optimal subproblem for part of speech tagging last week. The principle is very easy, right? Now with this principle, all you need to do is to build the table, right? WBE, right? B is from 1 to n minus 1, E is from 1 to n, to build this table. This table is called TB, maybe, build a table. But in addition to this table, okay, I call this table, okay. In addition to this table, you also need to have a BP back pointer, okay? So the back pointer table has the same size as the TB table, but each element in the BP back pointer table will point the B prime, okay, that leads to the optimal W hat BE. Okay, that's the principle. What is the size of this table? Well, You know the signature is B and E, right? So this B can range from 1 to n. This E can range from 1 to n. So this table must be n times n. Okay? So you can draw this table bottom up, left to right. So let me show you one example. The next slide shows you this table. Okay? We still use these 6 characters. Okay? Maybe the 6th character is 以前天下大乱. Okay? Okay. In the past, there was a chaos. Okay? So the first character is E. Okay? So this bottom left cell stores the highest scored subsequence, okay, where the last word is E. All right? Given this, we can move on to the next cell. First row, second column. What does it mean? It means the highest scored sequence where the last word is 以前. All right? This is easy to fill, right? We can move on to the first row, third column. It stores the highest word sequence where the last word is 以前天. Okay? Similarly, you can fill the first row, right? After you fill the first row, okay, where, okay, the whole, well, we only fill the first few characters as the first word, okay? We can move on to the second row. Second row starts from the second column, which means the highest word subsequence where the last word is 前, all right? It can only come from the first row, first column. It comes by adding the optimal subsequence ending with E with the score for the word bigram 以前, okay? And this is the optimal subsequence. Now similar, second row, second column shows you the high scored subsequence where the last word is 前天, right? It comes from first row, first column by adding the features from E, 前天, word bigram. All right. After you fill the second row, you fill the third row. Third row starts from the third column. Okay. Which means the highest scored subsequence where the last word is 天. Okay. And this subsequence can come from 2 cells, right? One is the highest scored one from the second column, right? Second row, second column. The highest scored sequence where the last word is 前. Or it can come from the first row, second column. The highest scored subsequence where the last word is 前天. 以前, sorry, 以前. Okay? So in the first case, you add the incremental feature 前 and 天. In the second case, you add the incremental feature 以前 and 天. From these 2 cases, you find the higher scored one to fill with 10. And you know you need to fill B prime, okay? Whether B prime is second row or first row, second column. So now you can summarize, right? Whenever you try to fill a cell in the ith column, you need to enumerate all cells from the I-1th column, right? And then you add the incremental feature and you compare, select the highest one, fill this cell, and put the corresponding row into B prime in the BP table. That's very similar to Viterbi, right? It's just that the nature is slightly different, so the dynamic program varies. Next, shows you the pseudocode. Okay, shows you the pseudocode. Basically, you just fill the table TB, and you fill the table BP by enumerating B, enumerating E, and then enumerating B prime. Right? So what's the time complexity? N to the power of 3, right? 3 loops. So this is more complicated than sequence labeling. You remember sequence labeling is, for first order case, linear. For second order case, also linear. but polynomial to the number of output labels. You know how you fill the table. In the textbook, you also have the second order case for sequence labeling, and I strongly recommend that you read it, right? Get familiar with the dynamic programs. How do you reduce cubic runtime complexity to linear runtime complexity? There's one trick, which I wrote. If you constrain that the output word size is at most m characters, your algorithm becomes linear. You can easily prove it. Okay, I skip it. This is the decoding for semi-CRF, which is also the same as the decoding for Perceptron and SVM, so I will not repeat this decoder for the other two models. Now let's look at how to parameterize, how to train a log linear model. So this is semi-CRF. So as you can remember, semi-CRF has the same activation function as for classification sequence labeling, CRF. It's a softmax, right? It's a softmax. But this softmax is a complicated one. A complicated softmax because the number of output is exponential, similar for sequence labeling. So you can use SGD to train this algorithm by MLE, right? Similar to last week. But we need to sort out a marginal probability issue. As you know, the gradient will consist of an expectation term, which is intractable. So we need to factorize that into cliques. So in order to train CRF, let's look at how to calculate marginal probabilities. So marginal probability is the probability of a particular segment being a word, right? Or a particular segment being two words. They're in principle the same. You know, similar to sequence labeling, this is a marginal probability. So if you treat the output word sequence as a joint event, then the one output word is a marginal event, okay? Right. So how do we do marginalization? We learned it, right? We just need to enumerate all possible other words, okay? All possible other segmentations, and then add up the joint probability, and we got the marginal probability. So this is what we learned in week 2. So how do we do that? We show in the middle equation, right? The probability of a word B to E, given the character sequence 1 to M, is the sum of all capital W word sequence belonging to Zhang 1 to N. Zhang means all possible segmentations, the set, okay? Such that B to E is one word, okay? The probability of the word sequence given the character sequence. And this equation describes what I just said. Okay, this is just a definition of marginal probability. Okay, and you know that we need to take the trick of dynamic program to calculate the exponential sum. How do we do that? So we look at the feature locality. And next slide, slide 39, shows the equation. I don't need to repeat, right? So you just factorize your global feature vector, and you extract out the summation of feature vector into the summation of scores. And then you further take down the summation from the exponential term as the product, okay, out of the exponential term. Now, this, okay, is the probability you try to summarize, or you try to sum up, okay. Next slide shows you two figures and an equation. The equation is the exponential sum, okay. In the sum, right, each term consists of the number of word minus 1 summations. How do you do exponential sum? We want to use dynamic program, right? And when we use dynamic program, the first figure shows you the scenario, which is we need to enumerate everything before B. We need to enumerate everything after E. And then we need to sum up this whole thing in the lattice, right? Subject that BE is one single word. You want to define a dynamic program to solve the problem. However, you have a junction in the middle, so that if you do it from left to right, you cannot finish it. If you do it from right to left, you cannot finish it. How did we solve the problem last week? You cut the whole thing into two halves, right? In the second figure, I show it. The first half sums up everything from the left until CBE, right? The second half sums everything from the right until CBE. And if you can figure out how you put the first half and second half together, right, as the first figure, you're done. Because single dimensional summations can be done efficiently. Okay, so let's do the split. Next slide shows you how to split exponential sum. Again, the trick is what? Distributivity, right? You first separate the product into two halves. One involving only something until E, from 1 to E. The other half involves everything from B to N, right? You split the product. And then you need to split the summation, right? This is an exponential sum. Exponential sum of products, you use distributivity. I proved to you last week, okay? When you use productivity, you can basically put everything until E together in the first term. You can put everything from B to N together as the second term. Two product. A sum of product now becomes the product of two sums of products. I leave it to you to prove it, okay? And needly to say, there's also a partition function Z to calculate. Now, next slide shows you the picture illustration of this equation. So suppose that CBE is C34, and 34, the two characters are a word, right? So you split the whole thing into a forward term and a backward term. The forward term is called alpha, the backward term is called beta. Now each one can be calculated incrementally. Next slide, alpha. Alpha can be derived very similar for sequence labeling, right? So it turns out that alpha B prime E prime is equal to the sum of B prime prime, alpha B prime prime B prime minus 1, and times the incremental score, okay? It's completely analogous to sequence labeling. I'll skip it. So next slide shows you a figure to illustrate how this incremental calculation is done, okay? So each incremental step, enumerate all possible B prime prime, and you sum everything up to calculate alpha B prime E prime, okay? And pseudocode is shown in the next slide. It turns out that this one draws you an alpha table, which is similar to the TB in the decoding algorithm we just discussed, okay? And the analogy between this forward algorithm and the decoding algorithm is the same or as the analogy between the forward algorithm and Viterbi algorithm for CRF. So I will skip it. Similarly, your beta term can be calculated incrementally, right? But this time from right to left. And next slide shows you pseudocode for the beta term. It's just a mirror of the alpha term. Okay, the algorithm framework is the same. Now, given alpha and beta, you can calculate the marginal probability as 1 over Z, alpha times beta. Okay, what is this Z? Z is the partition function, right? There's one way you can do it. Well, you can enumerate all possible B and E, right? Calculate alpha times beta. And then you add these scores together, that is Z, right? But you could also just directly calculate Z, because what is Z? Next slide shows you. The partition function is, Z is just like this. The sum of all possible W prime, right? E to the power of theta phi, okay? So this can be directly calculated using a dynamic program, which is shown in the next slide. Okay, so the next slide still draws a dynamic program table. I will skip it, but you can read the textbook. But no matter whether you use enumerating BE to calculate the normalization function, or you just use a dynamic program to calculate the exponential function, the sum function, the results are identical and the meaning intuition is the same, okay? Now, given this marginal probability, we can train semi-CRFs now. You just need to go to slide 52. So this is MLE with, okay, this is MLE, the definition of MLE. You maximize the log likelihood of the data set. It turns out to be the log likelihood in the last equation. And if you look at this equation, the shape is the same as for classification and as for sequence labeling, right? Only the definition of phi is different. So the next slide shows you slide 54 shows you the local gradient, okay? When we derive this local gradient, the whole process is the same as chapter 4 and chapter 8, so I skipped it. This is the third time we see exactly the same equation. But in the equation, there is something that's different between tasks. What is it? This expectation term, right? The expectation of global feature vectors over all possible outputs. Now for segmentation, this is no longer the same as for sequence labeling. For classification, it's just brute force enumeration, right? For sequence labeling, is to add all possible output sequences. But for segmentation, is to add all possible segment sequences. All right, this is exponential sum in expectation. But what can we do? We just follow sequence labeling. Next slide shows you. We first factorize the global feature vector into local features, okay? And then we take out the sum. We take out the sum. So it becomes the sum of all locations, the expectation of all sequences, the local feature vector at this location. And as you can intuitively understand, this expectation is also the sum of enumerating all possible local segmentations. The local bigram probability times this local feature, okay? So slide 56 shows us this equation, okay? So the equation is the sum of all possible bigrams, okay? The expectation of this bigram probability times the bigram feature, okay? And it turns out that calculating this local bigram probability is similar to calculating a local word probability. We can do this using a forward-backward algorithm. Okay, again, this is similar to the case of last week, so I go through this quickly. We can come to slide 60. So, which shows the local bigram probability. It is equal to alpha times beta times the bigram local score divided by z. So if you look at this, and if you look at last week, the equations are identical in the form, okay? But the meaning is different. All right. So after we calculate this local bigram probabilities, we can efficiently calculate the feature expectation term in the gradient. We can use SGD to train semi-CRF. Okay. Next, let's take a look at the large margin models from slide 65. And we know that large margin models include SVM and the perceptron. The parameterization scoring are the same as SVM. The decoding algorithms are the same. It's only that the training algorithm is different. Okay, the training algorithm is different. So we first look at the objective functions for perceptron and SVM. They stay the same for sequence segmentation as for sequence labeling. For perceptron, we require that the gold standard segment sequence is scored higher than all non-gold sequences. For SVM, we require that the gold output sequence is scored higher than all non-gold output sequences by a margin of 1. Okay? As a result, you can see that the the two training objectives are different. In addition, for SVM, you also have a regularization term in the beginning. Okay, so these are identical between sequence segmentation and sequence labeling. But the only thing that is different is that for both algorithms, you have a max S prime here, right? You have a max S prime here. What is it? It is to find the highest scored output sequence as a negative example if it is different from the gold. Okay, so here, for sequence segmentation, this finding of a max differs from for sequence labeling, right? Because the decoding algorithm is a different dynamic program. So this is the only place where a perceptron and SVM are not the same, okay, from sequence labeling. So the next slide shows you the perceptron pseudocode. You can see that only the row Z, okay, is equal to argmax. Only this row differs, okay. The other rows are all the same. Okay, and this also happens to the SGD training of SVM. Only the finding of the negative example differs. The rest of the algorithms are the same. Okay. With that, we have discussed everything I like for today. Okay. So in the textbook, okay, we discussed another thing, which is perceptron and beam search. And this thing is relevant to chapter 11. So let us discuss this in the week after next, okay? Next week, we go to yet another structured prediction problem, tree structured prediction, okay? So in the end, throughout this term, you will see 3 different kinds of structures. You will see how to apply the generative and discriminative models to that structure as well, okay? So see you next week.